Okay, we talked about sampling distributions when you have one sample. What I want to talk about now are situations where you're comparing means of two different samples. So I'm going to start with the case where the samples are actually independent. So this means there's two different groups, and picking from one group doesn't affect your choice from picking from the other. So we're going to deal with situations where indeed you're pairing elements. That will happen when we talk about paired samples in the future. But for now, let's say all our choices are independent. So here's an example of a situation that I'm talking about. So let's say we're worried about the curing times of cement. And there's two types of cement. There's deluxe cement and regular cement. And we're told that deluxe cement cures an hour faster than regular cement. And we're also given that the curing time of both cements has a standard deviation of 3 hours. So we know that somehow. We do a little test of each. We do 36 applications of the deluxe cement, and we measure the curing time, and we find it had a mean curing time of 5.4 hours. And the regular cement, in 64 applications, had a mean curing time of 6.1 hours. So we want a way to develop a sampling distribution of differences of means, and that's what we're going to do here. Once we develop the machinery, we'll go back and we'll talk about this data here. So what's really nice is that the central limit theorem here that we talked about in the previous lecture, saying that if we have a large sample size for a one sample sampling distribution, that the sampling distribution is normal, that idea applies for a two sample one as well. All you need is that both samples, N1 and N2, the size of them is still above 30. If that holds, then the sampling distribution is going to be approximately normal. And just like in the one sample case, we can say the mean is going to be the difference of the means of the populations. And the standard error is going to be a little bit different than what it is for the one sample case, but it does look quite similar. So it is indeed the variance of each of these squared over, this should be N1 and N2, the sample size. And that gives us our measure of spread in our sampling distribution, the standard error, of course. So this is the formula for calculating that. And you can show this mathematically, but that's beyond the scope of this course. For now, we can just think of this as a formula we can use in these cases. And this isn't anything you're going to have to remember, of course. You'll either have a cheat sheet or a formula sheet that will have these standard errors on it. So again, just to reiterate, if we have a population and we have some sort of mean and known standard deviation, and then we have a second population with the same thing, then if we draw samples of size N1 from population 1 and N2 from population 2, then that sampling distribution of the differences of the means of both populations, or of both samples, is approximately normal with the mean and standard error that we just talked about. Let's look at our previous example to look at how this works. So going back to our previous problem, we're not actually told the mean drying time of regular cement and deluxe cement, but we are told the difference. We're told that if we subtract the means, we should get 1. That the mean drying time for deluxe cement, which I labeled with a capital D, is 1 hour less than the mean drying time for regular cement. So that's what we're told here. And we did some sampling. We sampled 36 deluxe cement cases and 64 regular cement cases. And we found that in our sample that the mean time was 6.1 hours for regular cement and 5.4 hours for deluxe cement. We're also told the population standard deviations. We're told that the standard deviation of drying time of regular cement and deluxe cement is 3. So we have all our information. And using what we just talked about, we know our sampling distribution is going to be normal because we know both of these are above 30. Our sample sizes are large in both cases. Since they're large in both cases, the central limit theorem tells us that the sampling distribution is going to be normal. So we like that. When we have large samples, we really like that because there's not too much thinking to do. I will say, just like before, when our sample sizes are large, if we weren't given the standard deviations for the populations, if we just had them from our sample, well, when our sample size is nice and large, and for the purposes of this class, we'll say 30 and above, then we can use the sample standard deviation as a stand-in for the population standard deviation. The sample size is large enough that they'll be close enough for us to work with. In different books and in different courses and different applications, that rule might change, but for the purposes of this course, we'll say that when our sample size is large, we could use the sample standard deviation as a stand-in for population standard deviations. Okay, so we know, because both sample sizes are large, we know our sampling distribution of the differences is going to be normal. We like that. Okay, so all we need is the standard error for our sampling distribution. We have that via a formula. So that is just the square root of each of the standard deviations squared divided by sample sizes. So 3 squared over 64, that's for regular cement, and 3 squared over 36, that is for deluxe cement. And just to be clear, this is the same thing as standard deviation of our regular cement squared over the sample size of our regular cement plus the standard deviation of our deluxe cement squared, or the variance of our deluxe cement, over the number in our sample for deluxe cement. And if we calculate that, you can check, we're going to get 0.625 rounded to 3 decimal places. So the standard error, or sampling distribution standard deviation in this case, is roughly 0.625. Okay, so let's ask the following question. If the claim is true, remember the claim was that deluxe cement dried faster than a regular cement by 1 hour on average, so this is our claim. If the claim is true, what is the probability that the difference in sample curing times is at least our sample difference? Okay, so maybe let's calculate the sample difference right now so we have it. That's just, we'll keep the same order, that's really important. We have R minus D, so we'll keep the order of R minus D, regular minus deluxe. So this is going to be 6.1 minus 5.4, which is 0.7. Okay, so let's draw a diagram and then let's answer this question on the next page. Actually, let me change this a little bit. I'm going to change at least to at most, because maybe the claim of the manufacturer is wrong and the Lux cement doesn't cure as fast. So that's what we kind of want to ask. Does the Lux cement actually cure fast? So what's the probability that it doesn't? So let's look at that. So here's what our normal distribution looks like. So we have a mean difference of 1, or we're told that the difference is 1, and we have our sample of 0.7, and we're asked what's the probability that we get something to the left of it, that our mean curing time is at most 0.7. So let's highlight this in, maybe in the color green. This is the area we're looking for. And again, we don't have a table for this particular normal distribution, but we can always change it to the standard normal distribution by just looking at how many standard deviations you are away from the mean. So let's find the z-score of 0.7. So that's going to be our sample difference, the sample mean of R minus the sample mean of D, minus our mean difference, which we know is 1, but we'll write it out anyway, mu R minus mu D, over our standard error, which we calculated in the previous video, or previous slide. So we know this is 0.7. Our mean is 1, and our standard error we calculated is 0.625. And if we put that into our calculator, we get negative 0.48. So in the language of z-scores, of standard deviations or standard errors from the mean, 0.7 is 0.48 standard errors below the mean. So since this is a normal distribution, we standardize it. We want to know what the probability that z is less than 0.48 standard deviations below the mean. And we can look that up in our table. I'll draw a quick version of this table here. We're looking for negative 0.4, and here we want 0.08. And if we see where the column and the row match, we get 0.3156. So there is a 31.5 or 31.6% chance, roughly, that if we take a sample from the cements, that the difference will be 0.7 or less, roughly 31.6% of the time. So there's two other situations I want to talk about, and very similar to situations in the one sample case. Well, if our populations, at least one of them is non-normal, and at least one of our sample sizes is small, then there's not too much we can do, in fact. In that case, we just kind of have to give up. And by give up, I don't mean actually give up. I do mean that we have to use statistical techniques that are not going to be covered in this class. So you'd go out and you'd look that up, or maybe you'd contact a statistician who has a little more statistical knowledge. If the population is normal, well, we can still do things. In fact, just like before, we know that if the population is normal, we can do a t-distribution here. Or, in fact, we can still do a normal distribution, and we can use a normal distribution if we know the standard deviations of both populations. Then our standard error is going to be just like it was before. Square root of the standard deviation of the first population squared. Let me write that a little bit better. Standard deviation of the first population squared over n1 plus the standard deviation of the second population squared over n2, and then take the square root of all of that. And we can, of course, then proceed like before. With t-distributions, we have to be a little more careful. I'll explain this on the next slide. All right. If we are in a t-distribution setup, as explained on the last slide, there's kind of two cases. The first is when we can believe that the standard deviation of both populations, population 1 and population 2, are equal. We might be told that, or for some other reason, we might believe that's the case. In that case, we have the following standard errors and degrees of freedom to tell us which t-distribution to use. The formulas are a little bit complicated, but don't worry about them. It's not like you'll have to remember them. You'll just have to be used to calculating using them. So there's something called a pooled standard deviation, and there's a formula for the pooled variance, or the pooled standard deviation squared. And it looks like this: n1 minus 1 times the standard deviation of 1 squared, plus n2 minus 1 times the standard deviation of 2 squared, over n1 plus n2 minus 2. So that gives us our pooled variance, or our pooled standard deviation squared. And you just fill that in to our formula here to calculate our standard error. And similarly, if we have no reason to believe that the standard deviations are equal for both populations, well, then we just calculate the standard error very similarly to what we did in the normal distribution case. But the degrees of freedom for our t-distribution is going to be kind of, we'll call it a conservative estimate. In the book, and if you use a computer program, they use a little more complicated of a formula to determine the degrees of freedom. So we're always going to underestimate the degrees of freedom, or I should say we'll never overestimate the degrees of freedom. We may underestimate it. In fact, most of the times we will. And we'll just take the minimum of n1 minus 1 and n2 minus 1. So I just want to make a note here. This is a conservative estimate. And the reason I say it's conservative is because, like we've seen in a previous lecture with a t-distribution, as the degrees of freedom get smaller, it goes from a very broad, wide distribution to something resembling a normal distribution. And as the degrees of freedom goes to infinity, you get exactly a normal distribution. So when n is small, you get something a little more wider, with a little more error in the tails. So for the purposes of this section, all you need to do is be able to identify what situation you're in. We'll post some flowcharts you can follow so that it's easy enough to determine which distribution and which standard error to use. And if you need to determine which degrees of freedom, the formula to do that. So you don't need to worry too much about remembering these things. If you have the idea of sampling distributions, if you follow these flowcharts, you'll end up doing the right things.